So what I want to talk to you about today is some work that I've been doing with collaborators to forecast signals of some very classic dark matter models in upcoming gamma ray observations. So I know that people here think about all kinds of interesting and exotic dark matter candidates, but this talk is mostly going to be about WIMPs. So I first want to just give a little bit of an introduction about the puzzle of dark matter, how I see the landscape of dark matter scenarios at the moment, and then the sort of classic benchmark that is thermal freeze-out. I want to talk a little bit about that and the status of WIMPs based on current data. And then I want to give you a little bit of a sales pitch for upcoming ground-based gamma ray telescopes and the prospects that they have of being able to test the WIMP scenario over much or all of its natural mass range. Now, we can say, this early bit, you'll see that we can say a lot of fairly generic things fairly easily. Then in the second part of the talk, I want to show you some some upcoming work. This is not yet published. We're hoping to send the paper out for comments today. So maybe next week. I thought 2506 number is probably a little too optimistic, but maybe 2507 early on taking some classic benchmark WIMP models and understanding whether they can be tested at the Cherenkov Telescope Array Observatory, CTAO. Hope I will show you that while these models are conceptually very simple, actually doing the calculations is pretty complicated. And I'll give you a look at the tool sets that I and others have built up to do those calculations, but show you that when you put all the pieces together and ask, will we be able to test these at CTAO? The answer, I think, is yes, pretty comprehensively. And there is, and then at the end, I just want to talk about some work that I did last year about some issues that come up in these theoretical calculations that sometimes you find that if you do the calculation according to the standard pipeline, you find that the result violates unitarity, which is bad. This means that you are not conserving probability at some point in your calculation. So we have a prescription. So this is the most particle physics-y or quantum mechanics-y part of the talk, in that I will show you a simple prescription for ensuring that you conserve probability and do not violate unitarity. All right, so I'm not sure what the custom is here, but I'm happy for people to ask questions as I go, if that's okay with you. Oh, okay, great. All right, so let's get into it. So the big question, which I and probably a significant fraction of the room are excited about, is, what is dark matter? We have pretty good evidence that there is some component of the universe that doesn't scatter, emit, or absorb light, and really transparent matter might be a better term for it, but we're kind of stuck with the term dark at this point. But it does have mass, it does have gravity. When we say it's matter, we mean that it appears to behave like matter in terms of gravity and cosmology. It has the equation of state of matter through all the cosmological epochs that we can measure. The most precise piece of information that we know about the dark matter is how much of it there is. We have a percent level measurement that it's about 84% of the matter in the universe coming from the cosmic microwave background radiation. We also have a pretty good understanding of where it is and how it is distributed through the universe, particularly on large scales. Like this phrase that the dark matter forms the primordial scaffolding for the universe. This is a set of results from simulations by the Illustris collaboration, of which I am not a member. People in this room do much more work on simulations than I do, but these gorgeous simulations of our cosmos are capable of reproducing the observed large-scale structure that we see. And so the picture that we have of the cosmos is that there is this underlying slow-moving filamentary web of dark matter. These panels correspond to early times at the bottom of the page and later times at the top of the page. This filamentary web, there are points of high density in this filamentary web that grow in density as time goes on. Those regions attract gas, attract ordinary matter through their gravitational pull, and thus form the cradles of the stars and the galaxies, and eventually the planets, and eventually humanity. So when we look out at the night sky and we see the stars, we see the galaxies with observatories like the fantastic new Vera Rubin Observatory, all of that is sitting on top of an invisible superstructure of dark matter. And we are able to predict pretty accurately its properties, at least at large scales. Small scales are more difficult and still a very active avenue of research, as many people here know. So these are all positive statements about how dark matter behaves, how much of it there is, where it is, how it is distributed. Yeah, and this is one more piece. We, as kind of as a corollary of the previous statement, in most galaxies of our universe, we believe they're surrounded by large clouds or halos of dark matter, which was one of our initial clues to why it was there, to the fact that it was there in the first place. And then we have one other really important piece of information, which is that if it interacts with other particles except by gravity, it does so weakly or not at all. We know that due to the null results of many existing searches. And these pieces of information taken together are enough to tell us that we do not have an explanation for dark matter within the physics we understand within the standard model of particle physics. So that's the problem. When faced with this problem, you can immediately start to ask a bunch of other questions. So what is this stuff, being the central one? But you could subdivide that. Like, what is the dark matter made from? Are we talking about one new particle beyond the standard model? Are we talking about many different new particles? Are we talking about something that we might not usually think of as a particle at all, like tiny black holes left over from the beginning of the universe? Where did it come from? Where did this 84% number come from? Why is it that, not 99.999% or 0.1%? Does it actually interact with ordinary particles other than through gravity, or does it interact with itself? If so, what's the nature of those interactions? And I could keep on asking questions like this for a while. Now, when faced with a problem like this, particle theorists get creative. And so what happens is something like this. This is a cartoon drawn by my colleague Tim Tate as part of not the most recent snow mass planning process, but the previous snow mass planning process back in July 2013. And this is meant to be a sketch, an incomplete sketch of possible classes of scenarios for what dark matter could be. The idea is that everything within this red line is a possible class of ideas for dark matter, and everything outside the red line is a broader question or puzzle of physics beyond the standard model that dark matter might possibly connect to. So dark matter could be connected to fundamental symmetries of the universe, such as supersymmetry. It could be connected to extra dimensions beyond the 3 space dimensions and 1 time dimension that we usually think about. It could be related to modifications to the Higgs sector of the standard model, or to the neutrino sector of the standard model. If the dark matter is a QCD axion or something like it, it could solve the strong CP problem in the standard model, where the strong interactions seem to be really surprisingly CP conserving. It could be that dark matter is just the tip of the iceberg, that there are many new particles, whole new dark sectors. Dark matter could experience forces that we don't know about because the standard model particles don't feel them in the same way that dark matter doesn't appear to experience electromagnetism. So at present, there are a very wide range of ideas for what dark matter could be, many of which are well motivated, are interesting, seem totally feasible. So that's the good news. The bad news is that at present, all of these scenarios are consistent with the data that we have. All of these are capable of explaining the properties of dark matter that we went through roughly on the previous slide. And so our difficulty is not finding plausible ideas for what dark matter could be, but trying to figure out what the correct answer is, what is realized in our universe within this extremely large and complicated space of possible scenarios. Now, one thing that we can do, and one in which there is a lot of effort going on here, is try to better measure how dark matter is distributed through our galaxy and through our universe, and use that to, and there are parts of these class of scenarios and of other classes of scenarios that will lead to striking signals in the dark matter distribution. But there are also, unfortunately, many scenarios for which the observable dark matter distribution is going to look pretty much the same, where there is just a degeneracy. So the long-standing answer for how do we get at those scenarios is, let's try to search for non-gravitational interactions between dark matter and visible matter. We do not know if such interactions are present. Like if we did, that would be fantastic. But in many of these scenarios, such interactions are present and possibly detectable. And so we try to search for them. To the degree that we don't find them, we can set limitations on this space. So there are, of course, many, many, many ways to do this. But the class of such searches that I have mostly worked on and that in an astrophysics colloquium is most likely to be relevant to people in the audience is perhaps the class of searches known as indirect detection. So my tentative definition of this is as a search for signals of dark matter interactions where the way that you're doing it is you're measuring standard model particles and you're looking for a case where the relevant, so you're looking for non-gravitational dark matter interactions between the dark matter and something else by measuring standard model particles. But what makes it indirect is that the relevant dark matter interactions occurred outside the detector. Direct detection is you're looking for a standard model particle jumping because a dark matter particle came in and hit it. The jump happens inside your detector, so does the scattering. In accelerator searches, you smash standard model particles together, hoping to produce dark matter or other new particles. Again, the interaction happens inside your detector volume. But indirect detection, you have the entire universe as your volume in which the interactions may potentially happen. But what you're looking for is standard model particles that come to your detector downstream of that interaction. So the classic examples of indirect detection are searches for dark matter annihilation and dark matter decay and their products. So this is a cartoon of dark matter annihilation. Two dark matter particles come together, smash into each other, standard model particles are produced. These standard model particles, so SM just means standard model here, these standard model particles could in principle be anything that we know about. They could be W bosons, they could be Z bosons, they could be Higgs bosons, they could be quarks, they could be any of the leptons, muons, or taus, or electrons, or positrons. If instead of dark matter annihilation, or in addition to dark matter annihilation, we have dark matter decay, maybe the dark matter just decays with a lifetime longer than the age of the universe. That could similarly produce these standard model particles. Now, since we don't have a detector right there, we're probably not going to actually see a W boson. Most of the particles of the standard model decay promptly on astrophysical cosmological timescales. So what we're going to see instead is the decay product of these standard model particles. So these are the stable standard model particles: photons, electrons, positrons, protons, antiprotons, neutrinos, antineutrinos, possibly some nuclei and antinuclei in there. And so indirect detection searches can generally be classified by where am I looking? What part of the universe am I looking for the interactions in? And what kind of particles am I searching for? So of course, this isn't just annihilation and decay. There are other variations. You can search for production mechanisms like axion dark matter converting into photons, or vice versa, the absence of photons due to that loss. You can also potentially do sort of indirect detection, where instead of looking for the particles directly produced from dark matter interactions, you look for their downstream observable consequences. I've spent a fair amount of time thinking about cosmological impacts of dark matter and annihilation and decay. There, the interaction happened way back in the early universe. You're not seeing the direct particles from it. Instead, you look for their secondary effects. But in this talk, I'm going to focus on kind of the canonical example of indirect detection, which is dark matter annihilates into standard model stuff, which decays, producing photons. Can we see them? Okay, so perhaps I would argue like the most classic use case for indirect detection is the case of WIMPs. So let's talk a little bit about WIMPs. So these are possibly the longest standing dark matter candidate or class of dark matter candidates. They're certainly a very popular one. WIMP stands for weakly interacting massive particle. And the weakly here is a little bit ambiguous. Sometimes when people say WIMPs, by weak, they mean interacts with the standard model electroweak gauge bosons directly. So the dark matter has a charge under the standard model weak interactions. It couples directly to the W and Z bosons. Later in this talk, we will look at a bunch of benchmarks of this type. Sometimes when people say weakly, they just mean not very strong, such that you get the right abundance of dark matter in the early universe. So sometimes we define WIMPs by their production mechanism, which is thermal freeze out. So the picture here is that if dark matter interacts directly with the W and Z bosons, or interacts with the standard model with interactions of similar strength, then in the early universe, we expect that it was once in thermal equilibrium with the standard model. So dark matter particles couldn't convert to standard model particles and vice versa. And if this is the case, then we don't really care what happened prior to that equilibrium phase. Everything that happened really early in the universe was washed out, but at some point we got to this equilibrium phase, and then then things proceeded under the standard scenario. So let's talk about this. So in the standard thermal freeze-out scenario, there's an early phase where the dark matter and standard model are in thermal equilibrium, and also the temperature of the universe is hotter than the dark matter mass. The dark matter is a relativistic species, behaves like radiation, has a similar abundance to the standard model. This plot is going to show the co-moving number density of the dark matter as a function of a time coordinate on the x-axis. And this is a very classic plot from a textbook by Colburn-Turner. So once the temperature of the universe drops below the dark matter mass, the interactions that convert dark matter particles into standard model particles, such as these annihilation interactions, start to deplete it exponentially, just like in a Boltzmann distribution, there's an e to the minus m over t factor. So this part 2 of the curve, the dark matter density is just following this Boltzmann suppression. But because we live in an expanding universe, eventually the dark matter density drops to the point that effectively two dark matter particles can't find each other to annihilate before the expansion of the universe pulls them apart. Another way to say it is just like the time scale. Yeah, the time scale for annihilation becomes long relative to the Hubble time, or the annihilation, because of the reduced density, becomes inefficient enough that it can no longer keep the dark matter in equilibrium with the standard model. And so then we say that the annihilation freezes out, the dark matter abundance also freezes out, and we go from following this exponentially falling curve to this flat co-moving abundance. We say that dark matter is a thermal relic. The height of this line is the relic density, and it's inversely proportional to the annihilation cross-section. If we annihilate really effectively, we stay coupled for a long time, there's hardly any dark matter left in the early universe. If we don't annihilate very well at all, there'll be lots of dark matter left in the early universe. Overclose the universe, there is a Goldilocks line, which gets you the observed correct amount of dark matter. And the WIMP miracle is that you get the Goldilocks line right about if dark matter is roughly at the weak scale in the mass and has roughly weak scale couplings. But the mechanism works for other masses and couplings as well. So we can think about like what is the viable range for this mechanism. On one end, this works. Something like this can work for dark matter masses down to around 1 to 10 MeV. What goes wrong at 1 to 10 MeV, as worked out in detail by some of the people in this room, is that you tend to disrupt Big Bang nucleosynthesis that happens when the universe has a temperature of about an MeV. There are maybe some loopholes to this statement, but in general, you have to work a lot harder to get this thermal freeze-out scenario to work without messing up BBN once your mass scale gets below about 10 MeV. You can't be a 10 MeV dark matter getting the right abundance through this mechanism if you only couple to the W and Z bosons. There's a long-standing bound that says if your mass is lighter than about 2 GeV, you need new mediators, not just the W and Z bosons. That's one of the motivations for thinking about dark sectors at the MeV to GeV scale. Preserve this kind of thermal relic story, this dynamic mechanism of getting the right amount of dark matter, but you need a new light mediator to couple to the standard model. On the other end of the spectrum, which is going to be more what I talk about today, there's a general argument that the dark matter mass needs to be less than a couple of hundred TeV. Depending on the model, it can range from about 100 TeV to a PeV, in order for the annihilation cross-section to be potentially large enough to deplete the dark matter to this point. So let me say a little bit, so this is called the unitarity bound. Let me say a little bit about this because later in this talk, I'm going to come back to cases where unitarity is apparently violated, and that's a problem, right? So let's talk just a little bit about, okay, the one other thing about this thermal relic scenario is that because getting the right dark matter density fixes the annihilation cross-section in the early universe, if the annihilation cross-section of the present day is still what it was in the early universe, this gives you a pretty model-independent prediction for what the annihilation signal should look like in the present day. So it meshes very nicely with these indirect detection searches that I talked about. Okay, so let's just say a little bit about unitarity and what sets the upper limit on the mass window. So in quantum mechanics, we have a general rule that probability should be conserved, evolution is unitary. That sets a mass-dependent hard upper limit on any annihilation or scattering rate. It's coming from quantum mechanics. If you remember from your quantum mechanics classes, you get terms that go like 4 pi over k squared times sine squared of a phase shift, well, sine squared of a phase shift is less than or equal to 1, that's where this limit comes from. So what that limit, so if we break down the scattering or the annihilation into different partial waves, so L equals 0, L equals 1, L equals 2, and so on, then partial wave unitarity says the contribution of the cross-section in each partial wave has to satisfy this inequality, where K here is the momentum of, so here I'm assuming two particles of equal mass. We could write this in terms of reduced mass if we wanted to. But here K is the momentum of one of the particles in the center of mass frame. And this is, I'm making the statement in the non-relativistic case. So in the context of annihilation, that means that, so as my dark matter mass gets larger and larger, if the velocity of my dark matter particles is comparable, and it turns out at thermal freeze out, the velocity of the dark matter particles is not that far below 1 and is not very dependent on the mass of the particle, so you can take that roughly as fixed. This upper limit on the cross-section is going to scale like 1 over the dark matter mass squared. We need a specific cross-section to get the right amount of dark matter in the universe. In this thermal freeze-out context, once the mass gets too high, this is just an absolute bound that tells you cannot get the cross-section high enough. If you produce the dark matter in thermal equilibrium, you will always be left with too much of it in the late universe. So in the dark matter context, we can frame this as an upper limit on the mass, but what it really is an upper limit on the cross-section. And of course, if we want to think about dark matter at heavier mass, that's fine. It just means that you can't get it into thermal equilibrium with the standard model. Or if it is, you need like some way to get rid of it that is not annihilation, because the annihilation can never be fast enough. Okay. So like just maybe like put a pin in that, remember that, because I'm going to come back and talk again a bit about unitarity in the context of these limits on cross-section at the end. But okay, so that tells us that thermal freeze-out gives us this nice target range. There is a large but finite mass window in which this mechanism can work, from about the few MeV scale up to the few hundred TeV scale. So, okay, that's big, but it's a lot smaller than the overall possible range of masses for dark matter. It predicts an annihilation cross-section in the early universe, which numerically comes out to be about 2 × 10⁻26 centimeters cubed per second. Parametrically, this is related to 1 over the Planck mass times the temperature at matter radiation equality, which determines the amount of dark matter in the universe. In particle physics units, it's about 1 over 25 TeV squared. And so in the subset of these scenarios where this annihilation rate is the same at freeze out and in the present day, we have a really clean target to go look for with indirect detection searches. And so a question that I find interesting is just, can we test that characteristic cross-section if it persists to the present day? So where are we at the moment? This is a plot that I made a couple of years ago in the course of the snowmass process. This is a cartoon. It's putting a bunch of different constraints together, but it roughly tells us what the picture is. So the pink region, so y-axis here is the dark matter annihilation cross-section. That number that I said previously was around 2 to 3 × 10⁻26 centimeters cubed per second for a thermal relic. This orange line corresponds to that thermal relic cross-section. This is the dark matter mass in GeV on the x-axis. And so everything in this pink region we think is more or less ruled out by current observations. Everything in the green region is mostly going to be the focus of this talk. It's where we think we might be able to get to with not too far-term gamma ray telescopes. And the far-term forecast is a more optimistic version of the near-term forecast. So where we stand at the moment is that if we want to test this thermal relic cross-section for pretty much all final states except neutrinos, we can test that thermal relic cross-section up to mass scales from several tens to several hundreds of GeV in a pretty robust way. At these sort of tens to hundreds of GeV masses, these constraints are often coming from the Fermi Gamma Ray Space Telescope and from the AMSO2 telescope in orbit that measures the cosmic rays. At lower masses, there are stringent constraints from the cosmic microwave background, for example. So over the timescale of the next 10 years, there is one more on shelf. There are several proposals, some more on shelf than the others, for our large southern hemisphere ground-based gamma ray telescopes that can potentially test this thermorelic cross-section up to much higher mass scales. This was what we drew during SNOMAS. So this green line was a combination of forecasts from the Cherenkov Telescope Array Observatory and from the Southern Wide-Field Gamma Ray Observatory. This is the SWGO collaboration, which is the latter of those, just put out their science booklet a couple of weeks ago. And this is their updated forecast. So this is that thermorelic cross-section target dashed here. The blue line is a CTAO forecast for a particular dark matter annihilation channel, and their orange line is their SWGO 5-year forecast. And so like in this one, they now think that for this channel, they could potentially get up over 100 TeV in sensitivity with SWGO. Okay, so I would say, like we've probed a significant chunk of the region, but this gives me hope that in the not too distant future, we might be able to probe, or we might at least have sensitivity to almost all of it. Now, just a little aside here before I go on and talk about high energy gamma rays for the rest of the talk. You could say, okay, but what about dark matter masses below 10 GeV? I mean, you just told us that the thermorelic cross-section is ruled out below 10 GeV for basically every channel, but we certainly still talk about dark matter below 10 GeV. And so that is true. Like if we do these searches at high mass and we don't see anything, it is not going to mean that we can say, there is no dark matter below 100 TeV. That is not the case. This is testing a specific production scenario. Below 10 GeV, we have pretty robustly ruled out the thermorelic scenario where the cross-section today is the same as it was in the early universe. So the loophole is either the production mechanism isn't thermal freeze-out, or the annihilation cross-section at late times is different from a freeze-out. And this is fine. There are plenty of interesting models in this category, but it does constrain your model building. And it also means that, well, for indirect detection is no longer obviously the place where you have a potentially nice, clear, relatively model independent signal. The indirect detection cross-section is now highly model dependent. So there's a lot of effort going on to search for this lower mass range in direct detection and also at accelerators. Nonetheless, we could still do better at indirect detection in this mass gap. There is often said to be sort of an MEV gap in sensitivity to gamma rays, as shown in this plot, which is just looking at the sensitivity to point sources versus the energy of the gamma rays. There are a bunch of experiments, this is a subset, that have been proposed or at different stages. Grams is maybe, I think, the most advanced funding-wise. They have a prototype that's meant to be flying this year or next year on a balloon. So these are experiments that would try to improve this sensitivity in the MEV to GeV band. My excellent undergrad student, Kayla O'Donnell, who's going on to do a PhD at UIUC this year, led a nice paper with this last year where we sort of summarized the expected sensitivity of these telescopes to these MEV instruments. So if you want to hear more about that, let me know. But I want to focus now on the high energy gamma ray telescopes. So as I said, the two that I think have sort of best defined expected sensitivity are the Cherenkov Telescope Array, CTAO, and the Southern Wide-Field Gamma Ray Observatory, SWGO. CTAO is a lot further advanced. They have funding in place for their alpha configuration. Construction has started. And that construction is currently taking place, is going to continue taking place for the next few years. And they're going to have both the northern and southern hemisphere site. The northern hemisphere site is more advanced than the southern, but we really like the southern hemisphere sites for dark matter searches because they can see the inner part of the galaxy. They can see the galactic center and hence the inner part of the dark matter halo. CTAO is an air Cherenkov telescope array. So all of these gamma ray searches, the way that they work physically is they're looking for a high energy gamma ray to come in and hit the atmosphere, looking at the atmosphere as a detector. The way the air Cherenkov telescope works is that when that gamma ray hits the atmosphere, it produces a shower of secondary particles. As those particles travel through the atmosphere, they radiate Cherenkov radiation. So if you have a sensitive set of detectors on the ground, you can look for that Cherenkov radiation from the air shower. The other technology is water Cherenkov telescopes, where what you do is you have a bunch of water tanks on the surface and you look for not the Cherenkov radiation from the cascade, but the particles from the cascade, from the secondary particles from the cascade themselves to interact with your water tanks and produce Cherenkov radiation there. So The Cherenkov strategy is good for angular resolution, good for energy resolution. It requires the telescopes to point. These are not wide field of view instruments, but you can have very good instantaneous sensitivity, generally better than with the water Cherenkov strategy. The big advantage of the water Cherenkov strategy, and there's a current telescope called HAWK that implements this strategy, the air Cherenkov strategy, the current telescopes called HESS, Veritas, MAGIC. The water Cherenkov strategy allows you to do wide field of view observations. So you can look at a large part of the sky at a given time, and it's also better for somewhat higher energies. So it's sort of 100 GeV to PeV scale. So it allows for longer viewing of targets and better sensitivity to extended sources. So SWGO just put out their detailed science case. They have selected a site, which is in Chile. When they selected the site, which was late last year, they said construction could start as early as 2026. So far, it is an international collaboration. So far, they've had R&D funding from NSF. I do not know what that trajectory is going to look like in the current environment. I mean, yeah. I just don't know. But at least in principle, it's basically a bigger version of the HAWK telescope, which was built in Mexico and which has been very successful. We know how to build these things. It's just a matter of building them bigger and in the Southern Hemisphere and getting money to do so. There are a couple of other instruments that are where the science cases are less well developed. China has a water Cherenkov telescope called LASO, which is in the Northern Hemisphere, but can kind of see the galactic center, albeit at very high zenith angle. And they have an infil array called LACT. This is not very well documented online. There were some talks at conferences last year where people from LACT said that they were hoping to start taking data as early as this year. So that's very interesting, but there hasn't been much in terms of like detailed specs online. So we haven't done forecasts for that. There are also other strategies. There's an idea for a successor to the Fermi Gamma Ray Space Telescope, which is lower energies. But if you want to get below about the 10 GeV scale, you really need to be in space. These Cherenkov showers are not effective at lower energies, and the Fermi Gamma Ray Space Telescope has been fantastic there. So the APT is the most on-shell idea I've seen for a successor to Fermi, but I don't think it's that on-shell yet. They have a demonstrator scheduled for later this year. And of course, at very high energies, neutrino telescopes can also give important constraints. Okay, so that's my sort of generic pep talk that with experiments like these, we really do have we potentially will have sensitivity to this thermal relic scenario very generically over all or almost all of its natural mass range. But let's now talk about some specific examples within this class of models. Okay, so the benchmark I want to talk about is sometimes called the minimal dark matter models, but since now we're getting into the more detailed part of the talk, I just want to ask if anyone has questions at this stage. People happy? Okay, very good. All right. Okay, so now we're going to do some particle physics. Okay, so we can consider specific models that inhabit this space, and depending on your definition of simplicity, one relatively simple class of models that you might think about in this space is sort of the classic WIMP scenario that is what I feel you would come up with if you had just learned about the standard model and somebody said to you, what do you think dark matter could be? You might say, well, all right, I know that the standard model has this weak gauge group. I know that I want weak interactions, that's the W in WIMP. So what if I just added to the standard model an extra matter multiplet that was charged under the weak interactions? Okay, but not the U1 or the SU3 of the standard model. So this approach of just saying, let's just add new matter multiplets that so that are charged under the standard model SU2, that means they interact with the W and Z bosons. Let's see what happens if we do that. I'm going to focus in this talk and on our paper that is coming out on cases where these representations are odd in size, and I will explain what that means. There's also a class of even numbered representations. I expect we can do something very similar for that, but that might be the next paper. So the idea of minimal, so we add a new multiplet of particles to the standard model. you have, so parameters describing these theories, the first one is just how big is your representation. So this is what the spectrum of one of these multiplets looks like. There is a charge zero, for the odd numbered representations, there is a charge zero state, which is the dark matter. And then there is a slightly heavier state, which has charge plus or minus 1. And so if you were in the triplet representation, 3 total particles, that's where it would end. You have the charge 0 particle, the dark matter, you have the slightly heavier particles, we might call them like chi plus, chi minus, and chi naught. 3 triplet. That's also called the Wiener. It shows up in supersymmetry as the partner of the W boson. Okay, so that's the triplet. If we want to look at the next representation up, the quintuplet, that corresponds to, you have the dark matter, you have the charge plus or minus 1 particles, and then you have other partner particles, other charginos with total charge 2. So that's a quintuplet, 5 total particles. Okay, we can keep going up like this. You know, if we have the septuplet, that means we have charge plus or minus 3 particles. So we have the dark matter, but it also comes with these somewhat heavier partners. Now, because the interactions of these extra multiplets are just they interact with the W and Z bosons, we understand everything about how they interact. It's just completely set by standard model physics. The kinds of interaction vertices that you can have a particle with charge X coupled to a particle with charge X minus 1 and radiate a W boson, or you can have a particle with a given charge coupled to the Z boson or the photons, so long as they don't have charge 0. Charge 0 particles, the dark matter does not couple directly to the photon or to the Z, right? So those are the interactions. Like that's the model. Yeah, it won't be stupid, but go on.
So you have standard model, you have dark matter, and then you have these other things, which are not dark matter.
Yeah, these are. Yeah.
Do they not interact via gravity, or why are they not dark matter?
They would interact via gravity. The reason they're not dark matter is because if you put them out in the universe on their own, they'll decay to dark matter. So like if I have like this charge plus 1 thing, I've got a charge 0 thing, it can radiate off an off-shell W boson, transition into the charge 0 state, and the off-shell W boson will, you know, make some like pions and stuff. So yeah, they're absolutely there. In the early universe, they would definitely be around. In the late universe, you usually make the justified presumption that they've all decayed. Good question. All right, so this gives us like a discrete set of possible models. There's one other continuous parameter, which is how heavy is this multiplet? Like how massive, what is the characteristic mass scale? I've said there are mass splittings. These mass splittings are radiatively induced. They're rather small. So they're all of these states are going to be pretty similar in mass. I'll tell you what rather small means in a moment, but all these states are going to be pretty similar in mass. There's going to be some common mass scale that characterizes them all. So if you say, I want this to be the dark matter of the universe, then, and you know exactly what its interactions are, you can do the freeze out calculation that we just discussed as a function of the mass and find out what mass gives you the right annihilation cross-section to get you the right abundance. That fixes the mass. Now you're done. So now you just have a discrete set of 0 parameter models whose interactions are completely predicted. Now, okay, so you might then say, okay, but hang on, surely we've ruled this out, right? I mean, you may have read multiple stories over the years saying, are WIMPs dead? You know, dark matter experimentalists attempt to rule out WIMPs. So surely we have ruled out this strategy of just like, let's just add some weakly interacting multiplets and we know exactly how they interact and we've just fixed their mass by getting the right relic density. It turns out that through direct detection and through collider searches, we have ruled out 0 of these multiplets. So yes, now, okay, you should not take this to mean, man, why is direct detection useful at all for WIMPs then? We can't even find these really simple models. It turns out that these simple things are kind of uniquely hard to find in direct detection. If you say, for example, my dark matter is in some admixture of the multiplet, so like maybe it couples to the W bosons and also to the Higgs bosons, that actually makes it much easier to find in direct detection. So this is kind of a special case that is particularly hard to see. Nonetheless, it is a pretty simple special case. So this plot on the right is showing for the odd numbered representations that we just talked about, the mass at which you get the right relic density. Red here corresponds to the dark matter being a scalar, blue corresponds to it being a fermion. The y-axis is the cross-section relevant for direct detection, the x-axis is the mass. So first, masses at which you get the right relic density. For the triplet, we know this is about 2.5 TeV, tera electron volts. For the quintuplet, it's about 14 tera electron volts. And for the sevenplet, it's up more like at 50 TeV, and we keep going up from here. This plot goes up to the 13plet. That you can see the mass at which you would get the right relic density is a few hundred TeV. And at this point, everything that I said before about unitarity should be ringing some alarm bells for you. Okay, so above this, we think that you just can't get the right relic abundance, but also the degree to which our theory is like under full theoretical control is starting to break down pretty badly by the 13plet. So you take with a grain of salt. So those mass scales kind of immediately tell you this is going to be super hard at colliders. Like the LHC has a center of mass energy of 14 TeV. There is one object there, there is one representation on this plot that is even like in principle within the reach of the LHC. And 3 TeV purely weakly interacting particles are really hard to see at the LHC. You can constrain winos that are lighter than a few hundred GeV, but not at this 2.5 TeV scale that you need to get the right relic abundance. This lower panel is a forecast for a futuristic, awesome muon collider with 30 TeV center of mass energy. And this is looking at how well it would do at trying to find this quintuplet representation. This red band here is what you would need to get 100% of the dark matter through freeze out. And this is the sensitivity for a bunch of channels. This would be an amazing thing. It would be super futuristic. It would find the Wino and also the Higgsino, which is the 2-plet representations. But it's just really hard to get to these higher representations with colliders because they're so heavy. For direct detection, well, that's what this plot is for. So this is the scattering cross-section for direct detection. This gray line here is the neutrino floor, the limits of sensitivity. This is meant to be like the ultimate reach of LZ. And we can predict the signals precisely. Here's where all the signals sit. They're all above, the good news is they're all above the neutrino floor. So if we actually get all the way down to the neutrino floor, we should be able to rule out all these representations. For the even numbered representations, things are actually even more pessimistic. They're all slightly below the neutrino floor. But so, this is why we direct detection experiments are great. They legitimately have not gotten to these benchmarks yet. Yeah. Is it a coincidence that they're so close to the neutrino floor? Yes. Okay. As far as I know, yes. There is no it's if you just sort of work out parametrically rough. So their direct detection goes through a loop of W bosons. If you work out roughly what the scale of that should be, it is kind of close to the neutrino floor. But the even numbered representations in particular suffer from this nasty accidental cancellation between the one loop process involving W's and a 2-loop process involving coupling the gluons that just happen to almost entirely cancel each other out. And so they're below the neutrino floor. There's a paper from 2012 that pointed out this for the first time when at that point we didn't know the Higgs mass. And it shows the result as a function of the Higgs mass. And for most Higgs masses, it'd be totally fine. But at 125 GeV, this cancellation is really close. So yes, it may be that if you believe in a deity, you might imagine that they have fixed the Higgs mass specifically to be mean to dark matter direct detection experimentalists. But yeah. Okay, so direct detection is possible, but pretty hard. You really need to get down towards the neutrino floor. Colliders are probably impossible if you're in one of the higher representations. If you're at a TeV or 2 TeV, then it's not impossible. It's just hard. But you need a futuristic collider. So, but indirect detection can ride to save the day. There's the potential for really clean and striking indirect detection signal from annihilation producing gamma rays. These are definitely high enough mass that they would produce gamma rays that these Cherenkov telescopes can see. And furthermore, the W and Z mediated interactions actually can significantly enhance the annihilation rate. Okay, so here's another, so the basic mechanism for this is called the Sommerfeld enhancement. This isn't a new idea. It was pointed out that it applied to these models by Hisano and Ujiri back in 2004, 2003, and 2004. But the basic idea is just like if I have an electron and a positron, or a proton and electron, they interact with each other better because of the long-range interaction between them, right? Electrons and positrons at low velocities annihilate much more efficiently because of the long-range attractive interaction between them than they would if you turned that off or made it short range. So the way that we can describe this is that the dark matter particles experience a potential. that's mediated in this case by the W and Z bosons, but more generally could be by any like mediator that is light relative to the dark matter particles, that makes it more likely that you will find them close to each other, makes it more likely that they will annihilate. You can also think of this as basically being like gravitational focusing. It's a low velocity enhancement. It matters when the potential energy is large compared to the kinetic energy. If the kinetic energy is high to the potential compared to the potential energy, the particles will just fly past each other, not really paying much attention to the potential. But at low velocities, which is relevant for indirect detection in our halo, this can be important. And this was the calculation that Hisano and Nijiri did for the WINO. That's this triplet example back in 2003. They showed that as a function of the dark matter mass, and in particular, here's the thermal mass around 2 TeV, there are these large spikes in the annihilation signal, which can significantly enhance the cross-section. Okay, so that's very convenient for us. I'm going to go into a little more detail on how we do the calculation here, just because it's going to come up when I talk about how to make sure you preserve unitarity in this calculation. But this is also a place where if you don't follow this bit, it's not critical. So in practice, how you do this is you look at the interactions that the dark matter has with the mediator. You use those interactions to read off the potential that the dark matter experiences. So this is like the analog of the Coulomb potential for electromagnetism. It's usually in these cases a Yukawa potential that depends on the mass of the mediator. You solve the Schrodinger equation with this potential. You find the wave function of the two-body state of the two particles coming together. You have to assume they're non-relativistic for this to work. You say, okay, well, the annihilation should be, it corresponds to a high energy scale, it's short range. So we'll just look at the wave function of the two particle system at the origin. That will tell us the enhanced probability of finding the particles in contact with each other, and that will multiply the annihilation. That will multiply the annihilation amplitude. So its square will multiply the cross section. Okay, that's the standard method. It gives you, so if we were to plot this as a function of the force carrier mass divided by the dark matter mass, and the coupling, it gets you like contours like this of the enhancement factor, which as you see can easily be a couple of orders of magnitude. Now, in the multiplet cases I've been talking about, there's not just one mediator, right? There's the W and the Z and the gamma, and there's not just one dark matter state. Well, okay, there's one dark matter state, but there are other states in the multiplet. So in that case, the situation gets a little bit more complicated, but not much. So now we have to think about interactions like this. Two dark matter particles, which I've labeled chi-naught here, come in, they exchange a W boson, go into this chi plus, chi minus state. From there, they could exchange a photon or a Z boson, or they can exchange a W boson and go back to the chi-naught state. So now what we should think of this is our state is described by not just the two particles that you started with, but the possibility that they could excite into one of these higher charged states as they come together in the potential. So the wave function is going to be a vector that describes the probability of finding the particles in the like chi-naught state, or chi plus, chi minus, or if we're in a higher multiplet, chi plus plus, chi minus minus. Okay? We're going to write down a potential matrix which describes the couplings between these different states. So like in this example, this 2 delta M is the mass splitting between the lighter state and the heavier states. There's this alpha over R that corresponds to the Coulomb potential between the charged states. And there's a contribution that from the Z-mediated interactions between the charged states. And then these off-diagonal terms in the potential are describing how you go from the chi-naught state up to the chi plus, chi minus state, or vice versa. Okay. And so then we're still just going to solve the Schrodinger equation, but now our potential is a matrix and our wave function is a vector. But again, so now when we look at what is the value of the wave function at the origin, that's going to be a vector. We're going to have a matrix that describes how the chi-naught state annihilates, how the chi plus, chi minus state annihilates, how the chi plus plus, chi minus minus state annihilates, so on. We'll label that with a gamma here. And we're basically just going to contract that annihilation matrix with copies of this wave function vector on both sides. And that's going to give us the enhanced annihilation rate. Okay? So this is the standard method. There is a problem with this standard method, which causes it to sometimes violate unitarity, but I'll come back to that in a little bit. Okay? All right. I should just say, like, in order for you might be saying, like, wait, okay, but why? do I need to take into account all the possible higher charge states? Is there some limiting principle on this? So again, you can basically just see this from classical mechanics. You need the incoming particles to get enough energy from the potential to be able to scatter up to the charged states. So that means that you need the mass splitting to the charged states to be smaller than the potential energy. The potential energy is parametrically like the coupling squared times the dark matter mass. The mass splitting between the states in these minimal dark matter multiplets is parametrically the coupling times the mass of the W or the mass of the Z. So long as the mass of the dark matter is sufficiently heavier than the mass of the Z boson, then you can access these higher states through the potential. Okay, so that's how you do the Sommerfeld enhancement. There are a couple of, okay, and these are just some general statements about the Sommerfeld enhancement. This is pretty ubiquitous when you have long-range forces, by which we mean that the mediator mass is lighter than the inverse of the Bohr radius for the system. For weakly interacting dark matter, the coupling is about 1/30. The mediator mass is the W mass. Take it here. That means that this is going to matter when the dark matter mass is heavier than about 2.4 TeV. That describes every single one of these minimal dark matter representations that we just talked about. So it's always going to matter for them. It's most important at low velocities, so it's important for indirect detection. It can also be important at freeze out in the early universe, but the velocities are higher there, so it tends to matter less. Now, okay. You might be thinking, if I have a long-range potential between particles, could I get bound states as well as just enhancements to annihilation? The answer is yes. I'm not going to go through the bound state calculation in detail, but indeed, to get things right, you also need to take into account the production of bound states, both at freeze out and in the indirect detection context. There's one other thing that you also have to take into account to do the theory calculation right for these minimal dark matter models. So yeah, the first part of this is the good news is that the Sommerfeld enhancement and the fact that the potential lets you excite into these charged states means that now you're much better at annihilating your photons, because charged states love to annihilate your photons, right? So you can actually get a nice, clean, dramatic photon signal, and it would be a monochromatic Lion photon signal if the dark matter goes directly to 2 photons. So that's great. There's no background for that. But a subtlety, which Mariangela and I learned when we tried to do a similar project back in 2012, is that in the calculation of these rates, there is one more effect that you have to take into account, which is that some of the loop diagram, when you do the quantum field theory calculation, some of the loop diagrams get enhanced by large factors, and you have to do a complicated effective field theory calculation to resum those large logarithms. I am not going to go into that in detail, because that is a colloquium in its own. But I will say one cool thing about this. So we did this long and complicated calculation of how to sum up these loop diagrams for the WINO, for the three-plet, in gory detail, starting in 2014. It turns out that the WINO was a terrible example to start with, because the long and complicated answer that you get has a lot of factors that depend on the representation, and all our factors depended on the fact that it was in a three-plet representation. But so were the W and Z bosons. And so when we finally, a couple of years ago, did this calculation again for the quintuplet for a different representation, we found that actually all the complicated parts of the calculation only depend on what representation the W and Z bosons are in, which we know, and has nothing to do with the representation for the dark matter. So this line is for the particle physicists. If you're not a particle physicist, don't worry about what is going on here. But basically, you can describe the matrix element that you need for the hard annihilation. You can factorize it into 2 pieces. There is a long and complicated piece, but it only depends on the properties of the W and Z bosons. It has nothing to do with the dark matter representation. The part that depends on the dark matter representation is actually rather simple to calculate. So once we understood this, which we did a couple of years ago, we realized that we could just turn the crank, use the complicated results that we had worked out for the WINO, and just like adjust this small component that depended on the dark matter representation and get the answers for all the odd numbered minimal dark matter scenarios. So that's what we've done anyway. So this is the recipe that we've just talked about. We're going to solve the Schrodinger equation to determine the distortion of the wave function of the colliding particles and the spectrum of bound states in the theory. We're going to take into account the Sommerfeld enhancement and also the possibility that the dark matter particles could form a temporary bound state that then decays away into standard model particles. we're going to use these techniques of soft collinear effective theory that I haven't described, but I can say more about if people want, to compute the annihilation rate of the dark matter and the metastable bound states and the spectrum of gamma rays that we get as a result. And so we have this pipeline, and then we will just turn this crank for all the representations. So in work that should appear, I hope, in the next week or two, these are the results that we get for the, so this is, for example, the cross-section to make a monochromatic gamma ray line as a function of the dark matter mass for the 3-plet, 5-plet, 7-plet, 9-plet, 11-plet, and 13-plet minimal dark matter models. You see, like, these spikes are coming from the presence of the Sommerfeld enhancement and the bound states. The gray regions are showing the range in which you would get the right thermorelic abundance within the uncertainties of the calculation. You see that these uncertainties get much larger as you go up to these high multiplets. That's because these high multiplets are not under great theoretical control. Okay, so then we can take that. I see I'm getting to the end of my time. So then we can take that and say, okay, how is CTAO going to do at this? The CTAO collaboration has published a galactic center survey strategy. So we just adopted their galactic center survey strategy. This involves looking at a region of radius 2 degrees around the galactic center, masking out the central part of the galactic plane. And their survey strategy involves 9 pointings over this region with a total time of 500 hours, which would cover this region roughly uniformly. The background in this region, there is potentially an astrophysical diffuse background, with CTAO's current estimates of their instrumental, well, they have a background from cosmic rays hitting the atmosphere and producing Cherenkov showers that get misidentified as photons. At the current level of estimate for that background, we expect it to be that to be the dominant background in the region of interest. So we could be, I mean, we try to model this astro diffuse background, but it is subdominant, and errors in it probably aren't critical. So now we then have a critical question. Okay, we know per dark matter annihilation what kind of gamma rays we get, but how much dark matter do we have in the inner galaxy? This is the place where work by people in this room has been very helpful. So this is the key uncertainty in all indirect detection probes of the galactic center region. We wanted to try to get a conservative estimate for how much dark matter there could be. So we took 3 approaches. The first one is the one that we've done in previous papers. You can do this somewhat naive thing of just modeling the dark matter density distribution as a classic Einastro profile that then just goes dead flat within some core radius, RC. Okay. There was, so this upper panel is showing the dark matter density as a function of distance from the galactic center. So our naive Einastro core is like this black line that then goes to this dashed line here. The reason, so in this context, some studies of the bulge about 10 years ago suggested a band for the possible dark matter density within the bulge. Dan Hooper then took that and reconstructed it into, okay, if you had a chord profile, what would that imply for the core radius? And found that the bottom of the band corresponded to a core radius of roughly 2 kiloparsec. So there is an observational suggestion that probably your core size should be smaller than 2 kpc. Other approaches, so some of our colleagues have taken the approach of considering Milky Way analog galaxies from the Fire 2 simulations and looking at the range of profile that you get in those galaxies. The orange line and the purple line in this plot are showing the lowest and highest dark matter signal galaxies for this region of interest from that ensemble. So this is Thelma is the lowest one and Romulus is the highest one. There's also, we also used a recent analysis by Hussein et al., which is in this paper, where they used a number of different simulation suites to try to bracket the effect of baryonic feedback on the dark matter density. The result of their paper is this gray band here, is what they get for the expected range of profiles. If you convert that into asking how large should the signal be from the region that we look at, so this is this lower plot. So this J is the is effectively just parameterizing the size of the signal. The black line is showing what you would get with a chord Einastro profile as a function of the chord size. The orange line is just showing for calibration what you would get from Thelma or from Romulus, and the gray band is showing what you would get from this Hussein et al. Estimate. And it turns out that somewhat by coincidence, our like crude inastro profile with a 2 kiloparsec core corresponds pretty much exactly to the bottom of the band from Hussein et al. That's a total coincidence, but it meant that we didn't need to change very much about the plots, and is somewhat lower than what you would get from this ensemble of possibilities from Thelma. So when I say we can test these scenarios, what I'm going to mean is we can test these scenarios if the integrated dark matter density squared along the line of sight from this region of interest is at least as large as what you would get with a chord inastro profile, which also corresponds to being within the band from Hussein et al. And you know, within the range of possibilities that we see from the fire simulation. So with that, this is what the forecast constraints look like. We just use it. So at this point, the analysis is very simple. It's just a likelihood ratio method. It's more or less just looking at our signal over square root background in the region of interest. We tested both binned and unbinned approaches to check if that made a difference. It doesn't. So what this is showing is for each of the SU2 representations, the 3, the 5, the 7, the 9, the 11, and 13, each of these error bars is basically showing you what you would need the core size to be for the model to not be ruled out in the event that we don't see a signal. Okay, so for example, for the we know here, this is the 3-plet. So there are 3 different colors here. The first one is if we just include the gamma ray monochromatic line, and then the blue line is showing what happens if we also include lower energy photons produced by, say, making W bosons that then decay, and the orange line is when we add the effective bound states. For the we know, the bound states do nothing. But what you can see is that for any of these scenarios, even just for the pure lion, if you look at the inner galaxy with CTA and you don't see a lion, then you can rule out the we know unless the Milky Way has a 10 kiloparsec core. Okay. So as we go up to the higher representations, we see that for the 5-plet, you will also be able to rule this out. You should also be able to rule this out pretty safely. So you should look really at the orange line, which contains all the contributions to the photon spectrum. And you can see that for all of these, with the possible exception of the 13-plet, you will rule out these scenarios if CTA sees nothing, unless you have a core which is sort of 3 kpc or larger, or a profile that is not inastro but a core, but has a similar signal strength. The 13-plet is kind of right on the borderline. So if you're willing to believe in a 13-plet and also that you have a 2 kpc core, then maybe that will be consistent with CTA not seeing anything. However, I will say that the range of this band is coming from the fact that we don't really know the mass at which you get the right relic abundance for CTAO. So that being in that allowed region is relying on being right at the very bottom of one of these deep dips. So if you're anywhere like that is not fine-tuned to be right at the bottom of the deep dips, you'll be excluded in that case as well. Okay, so I am at the end of my time. I know, so I'm just going to very briefly, yeah, sorry, this one I evidently spent a little bit more time on this than I expected. I'm just going to tell you very briefly what the unitarity story is. So for heavy dark matter, you should be worrying about the breakdown of the perturbative treatment. And even at lower masses, those spikes in the cross-section induced by the Sommerfeld enhancement can violate the unitarity bound at the peaks of the spikes. That's bad. I'm always a little nervous when I do a calculation that sometimes it violates unitarity. It suggests that something is going wrong, and it's good to understand how it goes wrong or what. So it turns out that, this is just a statement that the resonances lead to a violation of unitarity. On the resonances, the enhancement scales light velocity as 1 over v squared, and that enhances sigma v. So sigma v goes like 1 over v squared, sigma goes like 1 over v cubed on resonances. But that's dangerous because you remember our unitarity bound went like 1 over k squared. So in the non-relativistic limit, that means our upper limit goes like 1 over v squared. If your cross-section goes like 1 over v cubed, eventually you're going to run into trouble. So what's the problem here? So physically, what's going on here is that the method I described for you for figuring out the Sommerfeld enhancement is you compute the wave function you figure out like the probability that you'll find the particles close together at short distances by computing the wave function. But when I computed the wave function, I completely ignored the fact that these particles could annihilate with each other, right? In a standard quantum mechanics calculation, the particles can't annihilate with each other. They go in, they scatter off each other, they go back out. But in this case, we have a probability sink at r equals 0, that sometimes when these particles come together, they just disappear from the perspective of the quantum mechanics problem. That, from the quantum mechanics problem, looks like non-unitary evolution. It looks like a loss of probability. 100% of the time the particles go in, but only 90% of the time do they come back out. The other 10% of the time, something else happens to them. So provided this is sufficiently small, it's not a bad approximation, it's an okay approximation. But when you're getting close to the unitarity bound for annihilation, that exactly corresponds to saying that the probability to annihilate is getting close to 1 when they get close together. So it is not a good approximation to simultaneously say that probability is 0 when it's 1. You get inconsistent results, you get apparent unitarity violation. We showed about 9 years ago how to do this in a simple case where you had only one dark matter candidate and you were looking only at the lowest partial wave. We did this just by like modeling the annihilation as a delta function that caused particles to disappear when it encountered at r equals 0. So in some recent work that I published with Aditya Parikh and Ryosuke Sato, so put on the archive last year, we're just finalizing the referee report now. What we did was said, okay, if the annihilation is short range, then you can still treat this mostly as like a normal quantum mechanics problem for all the radii outside some critical matching radius. Inside the matching radius, particles sometimes disappear. But outside that radius, it's just normal quantum mechanics. The particles are scattering off each other with no difficulties. So we can use the non-relativistic quantum mechanics for r greater than this matching radius, which we called A, but for smaller radii, we need to match onto an appropriate quantum field theory treatment. And this, we think this should just work for all partial waves and for all multi-state systems, but it does rely on this requirement that the annihilation is short range compared to the potential. This paper has an alternative method. This is only done for the single state case, but it doesn't seem to require the assumption that the annihilation is short range. Okay, so because I'm at the end of my time, I'm basically just going to, so I mean, that's the idea. It's just a matching problem. You just use the short scale physics to modify the boundary conditions for the quantum mechanics problem. You can describe the modification of the boundary conditions in terms of the short range matrix element. And what you get is a modification to the S matrix that looks like this. I think I'm going to go forward one more page. So this is the effect of doing this carefully, taking this into account properly. The short range matrix element gets corrected, gets modified by a contribution that comes purely from the long range potential. So we get like a correction to the effective short range matrix element, and also we get a correction to the Sommerfeld enhancement. So the modified Sommerfeld enhancement, the structure looks like this. Sigma naught L is what you would have gotten just by the standard method. P is just describing the momentum of the incoming particles. Kappa L describes the short range annihilation matrix element. So you can already see from this second correction why this fixes the unitarity violation. When the uncorrected Sommerfeld enhancement becomes really, really large, then the numerator of this blows up, but the denominator blows up more. This goes up by sigma naught squared. So instead of blowing up, this overall Sommerfeld enhancement gets squelched, like down to 0. So this prevents the unitarity violation. But something that we found that was kind of interesting, because I initially thought of this as just a way to, correct this unitarity violation. This first correction can actually be pretty substantial, even when your cross-section is not particularly close to unitarity. So this is just one example that we did for our we know dark matter sitting right on one of those resonances. This is looking at the cross-section as a function of velocity. This dotted line is the unitarity bound. This green line is what you would get doing the uncorrected calculation. Sorry, this blue line is what you would get doing the uncorrected calculation. So you go above the unitarity bound, and then eventually you flatten out and go back below it. The yellow is at a just slightly different mass range. And then the solid blue line is the corrected result. So what you see here is that now when you hit the unitarity bound, you stay consistently below it, but then the enhancement kind of saturates. with the result that if you're looking at these low velocities, the uncorrected cross-section is actually not above the unitarity bound. The uncorrected cross-section is fine, it's below unitarity. If you were just looking at this velocity, you wouldn't see anything wrong. But still the corrected cross-section is about 2 orders of magnitude below the uncorrected cross-section. So yeah, so in general, it's good to do things by methods that preserve unitarity.
Which relative velocities do you actually care about?
Good. So this is a toy example. This is not a phenomenologically relevant example because this is at about 2 TeV dark matter mass. And if you had 2 TeV dark matter annihilating at the unitarity bound, it would be super excluded. Like the sky would be burning in gamma rays. So yeah, so in reality, so the case where this is more likely to be phenomenologically relevant is a case where you are at much higher mass scales, where the unitarity bound corresponds to a much lower cross section, and you need to be much closer to it to get the right relic density. But yeah, you actually care about V of like 10 to the minus 3, 10 to the minus 4. So in this case, even like on the very tip of this resonance, this would be only just getting close to unitarity. But it's also like super excluded if at 2 TeV you have the unitarity cross section. Okay, sorry for going over time. I'll leave my summary there and take questions.
Further questions? Tracy?
So regarding the soft radiation correction that you mentioned, so I'm more familiar with this in the context of gravitational scattering.
Ah, okay, cool.
Where we're a little ways off from actually kind of probing these features directly in gravitational waves. But so are you saying that we actually probe the soft radiation or need to consider it for these dark matter detections?
Yes, yes. So the presence, so right. Okay, so when you say like soft radiation, are you talking about like the soft and collinear singularities that I mentioned? Yeah. Yeah, so what this does in the context of these dark matter models is it changes the shape of the spectrum around the endpoint. So instead of like just having a gamma, instead of just like having a gamma ray line, instead you have like a broad peak which comes from a collinear enhancement to the radiation, and then you have a tail extending to lower frequencies. That is CTA, so this, of course, how much you can see this depends on your energy resolution, but CTA is going to have a pretty good energy resolution. For SWGO, I expect it might be fine to just say, okay, this is basically all in a line cross-section, it's all close enough. But CTA's energy resolution is meant to be pretty good, and especially for higher masses, I think you do need to worry about this. I mean, of course, like the first thing to be would be just, do you see a signal at all, right? I mean, we haven't seen a signal from dark matter, but it is possible that if you, with a good energy resolution, if you fit it with a line and you're really looking at something significantly broader, you can miss a signal. Right. So it's, yeah, I mean, we think it's somewhat important to have the right spectral shape.
Good, thank you.
Thanks for the nice talk. I had a quick question about the matching between the QFT and the QM.
Yes.
So is the scale related to like the inverse mass of the dark matter? Okay.
Yeah.
And is it possible to do the entire thing in QFT like fully without matching?
So the problem with doing the entire thing in QFT is that right. So the problem with doing the entire thing in QFT is that the evolution under the long range potential is not perturbative. Okay, like, so if you try to do it, so if you try to do the whole thing in QFT, the Sommerfeld enhancement included, what you find is that your loop diagram, so let's just take the massless case, like the Coulombic case, that's the simplest one. Then you find that your loop diagrams get enhancements of alpha over B. So like you have a factor of alpha, but every factor of alpha comes with a 1 over b. So if your alpha is 10 to the minus 2 and the v you care about is 10 to the minus 3, then it's just uncontrolled. And I mean, so if you say, okay, all I care about is the ladder diagrams, I'm going to throw away all other diagrams, then this is the original derivation of the Sommerfeld enhancement. You can derive a Bethe-Salpeter equation, you can take the appropriate limit and so show that you get the Schrodinger equation with that potential. The way to do this like properly with systematically improvable corrections is to do a non-relativistic EFT treatment. In our paper, we did not do this carefully. We just said, work to some order, work to whatever order you want to take the potential for the Sommerfeld enhancement, match at leading order. We think that's probably okay at leading order. I'm somewhat interested in thinking about how to do this more systematically if you wanted to like make it systematically improvable and get the subleading corrections right. but we have not done it yet.
Oh, given the dark matter density consideration, I want to know, I'm wondering the Milky Way path of the TeV proton after interacting with the wing.
Hang on, sorry. So given the, yeah, okay, the mean free path of protons or photons?
Yeah, I want to know the mean free path of the TeV proton.
Protons.
Yeah.
Sorry, are you thinking like protons produced from the annihilation or the ambient protons in the gas? Yeah, so I think that I haven't actually put in the numbers, but like I expect that the scattering cross section for these WIMPs just hitting protons in the inner galaxy is, well, the scattering, that's the relevant cross section for direct detection. You're down near the neutrino floor at like 10 to the minus 47 square centimeters. I think that's going to be the typical WIMP never hits a proton. Just because like if you think about scenarios where we have constraints on dark matter baryon scattering from halos and from halo structure, those are normally more up at like 10 to the minus 30 square centimeters. So, I mean, they're many orders of magnitude higher than the cross sections relevant here. So I think these things are collisionless to a pretty good approximation in terms of how they interact with protons in the inner galaxy. That's it. I haven't done the calculation. I'm just like eyeballing. These are both lower number density and way lower cross section than the kinds of scenarios we usually think about for having DM baryon scattering. Yeah, it's an interesting question.